The title of this talk is Different Conceptions of Learning. It's by me and a PhD student of mine who unfortunately cannot be here because of visa issue, like several other people. I guess now we are already very familiar with this phenomenon that is many fundamental concepts have different understanding in this field. The same thing is true for learning. So that is already known in psychology. Actually, psychology learning has been used for several different phenomena, which is also the case in the machine learning community. I don't know how many people recognize this collection. It's one of the early collections machine learning work. If you take a look at those kind of collections, you will see many different understanding about learning. Okay? In the early days of machine learning study, in the early 80s. But if you pick a relatively recent textbook of machine learning like this one, it's an excellent book. But on the other hand, you will see that the learning have been basically converged to dominate interpretation. That's what I call algorithmic learning. Why? Because it's using an algorithm to learn an algorithm. What I mean, well, that's again, this is the picture taken from the textbook. Learning is taken to be an approach to solve a domain problem. The domain problem is itself is a mapping from some user-provided input to some output. But we need learning because we don't know the algorithm. So we need another algorithm, which is a meta algorithm or learning algorithm, to learn the algorithm we use to solve the domain problem. Okay? So the learning algorithm is doing some kind of meta-computation, take training data as input and produce a model as output. And then that model will later be used as an algorithm to solve the domain problem. Okay? So that's why I say this is basically using an algorithm to learn another algorithm. Symmetrically, we can see this as a function approximation typically. That is, this is the algorithm we want to learn. To learn it, we use the user data, we generalize it. Actually, yesterday I talked about this, more details in a deep learning workshop. So today's talk actually is the second half of that story. Okay? Yesterday I basically say what is the limitation of this type of machine learning, especially deep learning is a concrete example. And this part you are familiar, I'm not going to explain in detail. So what I'm going to suggest today is something some people asked yesterday, what is your solution? Okay, this is basically my solution. So I'm proposing a different understanding of learning, okay, which I call inferential learning, which again is actually not a new idea at all. You can find this kind of thing in early machine learning works. Okay? Like, for example, probably best known is Minkowski's work, but it's no longer in the current mainstream machine learning anymore. It's out of favor. This kind of learning, roughly speaking, is to take learning as listening. But what I mean, knowledge is represented as a statements, or you call it propositions, or sentence, whatever you call it. And then learning is carried out by a whole bunch of inference rules. So actually rules for non-deductive reasoning, like induction, abduction, analogy, and so on. And this has been studied before. And my system, NARS, which I gave a tutorial in the first day, Saturday afternoon, with a whole bunch of details, handles learning in this tradition. So again, on Saturday I talked about NARS in detail. Today is a very, very brief, very high-level overview as far as learning is concerned. So this thing is a reasoning system, but it's called a non-axiomatic reasoning system. Meaning is designed under the assumption that the system has insufficient knowledge and resources. Concretely, it means the system is finite, open to new information and new tasks, and it works in real time. It's a consequence. It means there is no absolute truth anymore. Everything is true to a degree. So, but on the other hand, it's still a formal, fully formalized and computerized reasoning system. Use formal language and formal rules. And another interesting property or special property is it tries to kind of like treat everything or almost everything as reasoning. Okay, many people say that's simply impossible or simply wrong. But you will see what we can do. Okay. So no time for detail, but since we're talking about learning, learning typically means to learn knowledge. So I will say that what kind of knowledge are there, or what kind of knowledge can be learned? There are several types of knowledge. There are some knowledge in the system which cannot be learned. That's the first category. You can call it built-in knowledge that's programmed into the system, or you can call it meta-level knowledge, okay? Which include, for example, grammar rules. Here, the grammar, I'm not talking about grammar of any natural language. That kind of thing needs to be learned. Okay? That's the grammar of so-called NARS. That's the native language of the system. That's built into the system. Also, all the inference rules are built in. They are not learned. And control algorithm, control mechanism, they are built in. Okay? And they are domain independent. On the other hand, all the domain dependent knowledge, or you can call it domain knowledge or empirical knowledge, they come from the system's experience. They are not programmed into the system. Of course, they need to be fed into the system somehow, okay? Either from user interface or use sensory motor and so on. Okay? Those kind of things are fed into the system and also is self-organized through a learning process in the system. And finally, there's actually something in between. Okay, we can actually turn, in the current version, we can already do that. We can turn some empirical or acquired knowledge into knowledge that can be built into the system in a different sense. That is, we can train the system, then we store the memory, and next time we reload the memory into the system. So to the kind of the second life of the system, the memory, the initial knowledge is kind of like built in, even though that's actually equivalent to some experience which happened before. Okay? So you have that kind of thing in between. So you can think that as compiled or compressed, but fundamentally they're basically the same as empirical knowledge. Actually, the true difference is all the empirical knowledge can be modified. The built-in knowledge cannot. So now, since built-in knowledge cannot be learned, we don't need to talk about them, so I will focus on empirical knowledge. The system uses a so-called term logic, where a term is an internal identifier of a concept, or the name of a concept. It represents an item in the system's experience, or the pattern in the system's experience. Be careful, this is not the traditional symbol in so-called symbolic AI. Because a term, for example, it can correspond to an image, no problem about that. Okay. So it's just the name of some kind of data that happened in the system's experience. Then we have belief. What we call belief are the conceptual relationships or the relations between the terms. And everything is true to a degree, as I already said. So there is a measurement which indicate evidential support for that relationship, which also I explained in the first stage tutorial. Then we have something called a task. That's what the system can do. There can be three types of tasks in the current implementation. It can be a piece of new knowledge to be integrated, to be absorbed into the memory, or it can be a question to be answered, or a goal to be actually achieved through the system's operations. So graphically speaking, the system's memory, you can see that as a conceptual network. Okay. Here, every node is a term, every link is a belief. Then you see there is numbers attached, that's the truth value or evidential support. And you have the white links, that's kind of what I call belief. There are the red links, that's the task to be processed. So again, this is explained in detail in the tutorial. So today I will just say, okay, if this is a content of the system, what kind of learning can happen? Well, you'll see that as far as domain knowledge is concerned, learning basically means to modify this network. Okay. So there are several types of things. The most common situation is, since this is a reasoning system, each time you'll see again the working procedure and the overall architecture also is explained in detail during the tutorial. So I'm going to skip that. But basically what it says is each time it's going to pick a node. If we go back to this picture, and it will pick two links from that node and use them as premise to build a new one. Since this is a term logic, it uses stochastic reasoning rules, which require that kind of pattern. And also at the same time, some of the rules, not only it will create new links, it will also create new nodes. We have explanation in the paper about that. So you'll see the whole topological structure of the network is going to change. It's a consequence of both the reasoning activity as well as the input. Whenever you add something into it, you add new nodes and you add new links. Furthermore, there is a third type of learning which you cannot directly see in the picture. That is, all the nodes and links has a priority value attached to it. Because since the system does not have sufficient resource, it's not going to pay attention to all of them equally. Some of them are more active, some of them are less active. So you can call them structural knowledge. That is, whenever I mention a term, what property you think about it first. Okay, which task you will pay attention, which task you will not pay attention. So when we say the system can do learning, it basically means all these three types of things. You see, the topological structure can be changed by reasoning activity. All the truth values, activation values, or priority values, whatever you call them, will be changed as a result of reasoning. Okay. So then what I want to stress, well, skip all those. Interesting property is, in this model, reasoning and learning is the same thing. It's exactly the same process. Is there still a difference? Of course there is a difference. Well, these two terms actually focus on different aspects of the process. If you analyze each step in detail, you'll see, oh, that's reasoning. Okay, you have premise, you have consequence. But if you step back one step, you see the overall structure. You see the long-term consequence. What you see is learning. Because all the small activities change our topological structure as well as all the parameters associated with it. Oh, that's what learning is about. There is nothing else. Okay. So this is not only for this two property, that's actually an example of many other things in NARS. That's what to me, that's what AGI is about. It's one process for almost everything. And those differences still exist, but there are different aspects of the same underlying process. So that's what we have been doing. So that's already said. Some interesting property I discussed in my paper, so you can take a look. For example, there are a lot of things discussed in the current machine learning community. Say one-shot learning, incremental learning, anytime learning, online learning, lifelong learning, and so on. I told you from day one, NARS are all of them altogether. They're not additional property to be added into the learning process. So if you see learning as the process I explained, you will see all those properties are already there. Okay. So I'm not saying that traditional machine learning is bad. I say that learning can have different interpretations, and each of it has its strengths and weakness. Of course, for many things, traditional machine learning or mainstream machine learning does better than my model. I agree with that. Okay? But I don't want people to be too narrow-minded to say, oh, that's what learning should be done, or that's how learning is defined. To me, that is wrong. Okay, that's all.